Hey, this is Presh Talwalkar. Recently, Mind Your Decisions passed 3.14 million subscribers. I am so thankful for your support, and I wanted to commemorate passing pi million subscribers with a video about pi. Pi, of course, is the ratio of a circle's circumference c to its diameter d. While pi is defined in terms of a ratio, the number itself is irrational. The decimal representation of pi is infinite and never repeating. Pi can never perfectly be expressed as a fraction a over b, where a and b are integers. While no fraction of integers can perfectly represent pi, that didn't stop ancient cultures from getting close approximations which would be used for practical purposes. Famously, around the year 250 BCE, Archimedes came up with the following idea. If a circle had a diameter d equal to 1, then its circumference c would be equal to pi. So all he would need to do is construct a circle with the diameter 1 and estimate its circumference. Here's how he did it. He sandwiched the circle between two hexagons. The perimeter of the inner hexagon would be less than the circumference of the circle, and that of the circumscribed hexagon would be larger than that of the circle. He then kept doubling the sides more and more until he got to a 96-sided polygon, which is nearly the shape of a circle. From here, he estimated that pi would be between 223 over 71 and 22 over 7. This is one place where we get the famous approximation that pi is approximately 22 over 7, which is accurate to 2 decimal places, so pi is approximately 3.14. 22 over 7 is the most famous approximation to pi, and it reflects the universal nature of mathematics, and it was independently discovered in many cultures, including ancient Egypt, China, and India. But what most people don't know is there was an even more accurate approximation to pi that has been known since ancient times. And there's an incredibly easy way to remember it. Write the first 3 odd numbers twice. 113355. Split the digits right down the middle and form 2 different numbers. Take the ratio of the larger number to the smaller number. The fraction 355 divided by 113 is approximately equal to 3.141592, and this is accurate to 6 decimal places. To get a sense of how accurate this value is, let's plot these values on a number line. Let's first look at the scale of whole numbers. X is equal to pi is just larger than x is equal to 3. If we then plot the line x is equal to 22 over 7, the line goes right above x is equal to pi. The approximation is virtually indistinguishable from the actual value. It's only when we zoom in closer to the 3rd decimal place that we see some difference between the real value and the approximate value. But now, let's plot x is equal to 355 over 113. The line goes right above x is equal to pi. We can keep zooming in, and now x is equal to 22 over 7 is outside of the window, but x is equal to 355 over 113 is right over the actual value. It is not until we zoom in to the 7th decimal place that we see any difference between the approximation and the actual value. But where does this incredibly accurate approximation for pi come from? Some 15 years ago, the mathematician David Bow was wondering this very thing on March 14th, also known as Pi Day. He titled the post, "The Mystery of 355 over 113. Does this fraction relate to any of the famous formulas we know for pi?" So he started brainstorming. One of the famous formulas is the Wallace product, which is a truly remarkable formula. It's an infinite product for pi that depends on the even and odd numbers. So in any of these partial products, will we get the fraction 355 over 113? So let's get started. If we look at the first partial product, we get that pi is approximately equal to 4. We can then just continue term by term, and see if any of the partial products will give us the fraction 355 over 113. Alas, none of these fractions will be equal to 355 over 113, and therefore this fraction is not to be found directly in the Wallace product. But let's continue with another famous formula. Here is an infinite summation that is equal to pi. It was discovered by Madhava. It's sometimes wrongly attributed to Leibniz or Gregory. Pi is equal to 4 times 1 over 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus 1 over 9, and so on. We have an alternating sum of the odd numbers. What happens if we looked at any of the partial sums? The first partial sum will be equal to 4 times 1 over 1, so pi is approximately equal to 4. We then continue looking at the partial sums, and we see if any of these will give us 355 over 113. Alas, we will not get the fraction 355 over 113, so it's not to be found in the Madhava infinite series for pi. Bao then continues the article by thinking about Gauss's continued fraction for arctangent. He looked at these partial sums, and it converges very fast, but once again, we don't have the fraction 355 over 113. In 1999, Lange developed an elegant expression for pi based on the continued fraction for arcsine, but once again, 355 over 113 does not appear. So where does the fraction 355 over 113 come from? Before I get into too much mathematical details, I want to give a summary of the facts. Historically, the fraction 355 over 113 was calculated by Chongzhi around the year 480 CE, and this was a closer value than the approximation 22 over 7. Chongzhi's work was based upon two other mathematicians' works. One was Liu Hui, who came up with an ingenious area calculation to estimate pi. It was also based on the work of Chengtian, who developed an ingenious method of fraction interpolation. To get some perspective on how great Chongzhi's work was, his estimate of pi in the year 480 was a world record to 7 decimal places. It blew the previous record out, which was just 3 decimal places. This record would not be surpassed for more than 900 years when Madhava discovered an infinite power series expansion and calculated pi to 10 decimal places. So now let's go into the mathematical details and consider Liu Hui's pi algorithm. As mentioned earlier in the video, pi is equal to the ratio of a circle's circumference to its diameter. Archimedes thought about setting a circle with a diameter equal to 1, and he would calculate the length of the circumference, which is equal to pi. He would sandwich the circumference between inscribed and circumscribed polygons, and by doubling the sides until n is equal to 96, he came up with the estimate that pi is approximately equal to 22 over 7, or 3.14. So generally, the attitude was to consider the length of the circumference. But Liu Hui thought about it differently. Liu Hui first did inscribe a regular hexagon in the circle. But instead of considering the perimeter of the hexagon as an estimate for the circumference, he thought about the area of the hexagon versus the area of the circle. A hexagon can be divided into 6 equilateral triangles. On each triangle, he could construct another triangle between the hexagon and the circle. What would happen if he took all of these areas and rearranged them? This would give an estimate for the area of the circle. So he thought about rearranging these shapes to come up with another shape. Let's say he took these 3 red triangles and he just spread them out like wings and put them in a straight line. He could then fill in the gaps with 2 of the blue triangles. Then he could cut 1 blue triangle in half and fill up the other gaps. Now let's rearrange these hexagons. We can take these top 3 hexagons and just attach them to one of the blue triangles, and then we can attach 2 more of these hexagons here, split this hexagon in half, and cover up the ends of this diagram. So now the area of the inscribed polygon plus these triangles is exactly equal to the area of the shape we have just created, which is looking like a rectangle. So let's try to calculate the area of this shape. We know that its height will be the length of the height of a green triangle plus the height of a blue triangle, and this is exactly equal to the radius r of the circle. So one dimension is equal to r. What is the width of this rectangle? It's exactly equal to the lengths of 3 of the equilateral triangles. So by itself, this doesn't seem like an important dimension. But Liu Hui thought about increasing the number of sides of the inscribed polygon. If the number of sides keep increasing, eventually the sum of the side lengths halfway around will be equal to half of the circle's circumference. So what's the area of this rectangle? It will be equal to the product of its dimensions. So we have 1/2 c times r. But now c is equal to 2 pi r. Substituting in, we get 1/2 2 pi r times r, and this all simplifies to be pi r squared. And this is how Liu Hui came up with the area of a circle as pi r squared. So now equipped with the area of a circle as pi r squared, Liu Hui thought about estimating the area of a circle with the radius equal to 1, and that area will be equal to pi. So how did he estimate the area of a circle with the radius equal to 1? He first thought about inscribing a regular polygon with n sides. In this case, a hexagon is shown, so let's just denote the area of this shape as an. He then doubled the number of sides as an inscribed regular polygon, and we have the area of twice the number of sides, and we will denote that as a 2n. Now let's overlap both of these shapes. The shape with more sides will have more area. So what's the difference in areas between these two shapes? In this particular example, it will be equal to the area of these 6 triangles together. In general, there will be n such triangles. Now comes the truly ingenious step. Between each red triangle and the circle, there is still a tiny amount of area. So Liu Hui thought about how to fill in that area. He thought about creating a bounding rectangle on each triangle in a truly remarkable way. So split each of these red triangles down the middle. Let's just take this top triangle for example, and then rotate these triangles so that we form a bounding rectangle. Not only have we covered up the area that was missing between the triangle and the circle, but we have covered up areas outside of the circle. So let's do this for all of these triangles. So we now have a shape that completely covers up the circle and covers up some area outside of the circle. So that means we can estimate an upper bound for the area of the circle. We have the area of the green shape plus all of the areas of these red triangles. So we know that if we take the areas of the green shape and the areas of all of these red triangles, that will overestimate the area of the circle. So the area of the circle will be less than a2n plus d2n. But we can also estimate a lower bound. Of course, the blue inscribed polygon will be less than the area of the circle, so an will be less than the area of the circle. Liu Hui used this equation to estimate pi. In one case, he used a polygon that had 96 sides to end up with an estimate that pi was approximately 3.1416. Zhu Chongzhi built upon this method with a polygon of 12,228 sides, which is truly remarkable because they didn't have modern computation techniques. They were using something like counting rods, and he came up with an approximation for pi that was accurate to 7 decimal places. So it was truly a remarkable algorithm to consider the areas instead of considering lengths. To give you a perspective on how great these approximations were, let's look at the chronology of pi computation in Wikipedia. So the first major result was from Archimedes around 250 BC, and Archimedes came up with an estimate of 22/7, which was accurate to 2 decimal places. It took hundreds of years for Ptolemy to get to 3 decimal places, and then Liu Hui independently came up with an estimate that was accurate to 3 decimal places. This now brings us to Chongzhi, who in 480 estimated pi accurate to 7 decimal places. He also came up with the fraction 355/113. This was such an incredible record that it wasn't surpassed for more than 900 years later when Madhava came up with the infinite power series expansion, which gave him a record of 10 decimal places. I also want to give a shout out to the next entry in 1424, which was Al-Kashi, who used Archimedes' method on a tremendously large polygon to come up with pi accurate to 16 decimal places. But these records are in terms of decimal values, so how did Chongzhi come up with the fraction of 355/113? We have to take a step back to understand Chengtian's inequality. So let's say we have pi as approximately 3.1416. We could say that pi is between 3 and 4. We could put these as fractions that pi is between 3/1 and 4/1. We now need some way that we can come up with another fraction that's between these two bounds that'll somehow definitely be in the middle. Once we get another fraction in the middle, we can then iterate this and keep getting other fractions that'll be closer and closer, having a lower bound and an upper bound for pi. So this is where Chengtian's inequality comes in. Let's say we have whole positive numbers a, b, c, and d. So these are whole numbers greater than 0. Say we have one fraction a and b, and let's just put it in lowest terms. Let's say AB is less than C/D, and C/D is also in lowest terms. What happens if we take these two fractions and we add the numerators and add the denominators? We end up with a new fraction called the mediant, and this is equal to A plus C divided by B plus D. The remarkable thing is that this fraction will always be in the middle of the other two fractions. This is Chengtian's inequality. There are two ways to understand this. Let's take a look at this from a statistics perspective. Imagine you're playing a sport and you have points, you have number of games played, and you will have an average number of points for those games. Imagine you end up scoring A points for B games. What will be the average number of points per game? It will be equal to A/B. Now, let's consider you play some more games. Let's say you score C points in D games. In that stretch of games, your average will be C/D. But now, let's consider the total average. So how many total points have you scored? It will be equal to A plus C. The total number of games will be equal to B plus D, and your total average over all of these games will be the total points A plus C divided by the total number of games. So this mediant is exactly equal to the weighted average of the other averages. If you have a weighted average, it's going to be in between the two things you're taking an average of. It will just be depending on the weights. The first average, A/B, will be weighted by the number of games that it represents, which is B divided by the total B plus D. And we add on the other average, C/D, times the weight, which will be D/B plus D. So one way of understanding this will be in the middle is by considering it as a weighted average. But there's also a nice visual way to see this. Let's think about a graph. Let's have a vector, which is the point B comma A. What is the slope of this vector? It will be equal to A/B. Let's plot another vector at the point D comma C. The slope of this line will be equal to C/D. Now let's add these two vectors together. So let's just add this vector and let's form a parallelogram. The sum of these two vectors will be this endpoint. Now what are the coordinates of this? We can add up the x coordinates and the y coordinates, and this point will be B plus D comma, a plus c. What's the slope of this line? It will be equal to a plus c divided by b plus d. And notice this vector is right in the middle. That is, the slope of this line is larger than a over b, but it will be less steep than c over d. And that's how a plus c over b plus d is exactly in the middle of these two fractions. We can now use this inequality to get fractions that are closer and closer to some number. So let's say we have an interval where we have a over b on the left, c over d on the right, and we have some number x that we know is in between a over b and c over d. We want to develop fractions that are closer and closer to x. How can we do that? Well, we know that the mediant will always be somewhere in the middle of this interval. Now, we don't necessarily know where it will be relative to x, but one possibility is that it will be larger than x. So let's just say a plus c over b plus d is over here. We can then come up with a new interval where we say this is the upper bound. So we create a new interval where a over b is on the left, we have x somewhere in the middle, and we have a plus c over b plus d on the right-hand side. But we're not done yet. We now have a new interval. We know that each endpoint is a fraction, so we can replace this upper endpoint as a fraction, and let's call it c prime over d prime. We then can use Chengtian's inequality on this new fraction. Now we know that this mediant will be somewhere in the middle, and let's say that it's between a over b and x, so that this will be on the left side of x. We can then create this as the new interval where this is the lower bound, and once again we can keep repeating this process. We will change that this lower bound will be some fraction a prime over b prime, and we will repeat the process so we get closer and closer fractions to this value x that we're trying to approximate. We are now equipped to derive the fraction 355 over 113. We start out with Liu Hui's approximation for pi, which is 3.1416. A first step is to say that this value is between 3 over 1 and 4 over 1. We now take these two fractions and we add up the numerators and add up the denominators, and this value will be equal to 7 over 2. How does that compare to the approximation for pi? Well, 7 over 2 is equal to 3.5, which is greater than the approximation for pi. So 3.5 will replace 4 over 1 as the upper bound. So we will come up with a new interval where we have 3 over 1 is less than pi is less than 7 over 2. We now repeat the process on this interval. We take the two fractions and we add up the numerators and add up the denominators. This gives 10 over 3, which is approximately equal to 3.3, and once again, this is larger than pi. So this is going to be the new upper bound. So the new interval will be 3 over 1 is less than pi is less than 10 over 3. So let's do another example with this interval. We will take these two fractions and we will add up the numerators and add up the denominators. We get the new fraction 13 over 4. That's equal to 3.25, which once again is greater than our approximation for pi. So this becomes the new upper bound. We can continue doing more and more interpolations. In the next round of interpolation, we will end up with 16 over 5 as the new upper bound. Then we end up with the upper bound of 19 over 6. From here, we end up with the new upper bound of 22 over 7, and we have come to the most famous approximation for pi. What happens if we continue one more round? If we add up the numerators and the denominators, we get 25 over 8, which is equal to 3.125, and that is less than our known approximate value for pi. Now, 25 over 8 will become the new lower bound. In fact, in all of the remaining cases, 22 over 7 is going to remain the upper bound. So from here, we're going to keep improving the lower bound, and we're going to keep getting new fractions. From here, let me just show you the new bounds in each interval. This would be an entirely tedious process to do without modern computation techniques. It is truly amazing what Chongzhi was able to do. If we continue the calculation until the 22nd iteration, we end up that 355 over 113 is less than, our approximation for pi, is less than 22 over 7. So we have now derived that pi is approximately equal to 355 over 113. It is truly a remarkable achievement of ancient times, and I hope this video will make it clear where this fraction comes from, so 355 over 113 will be a mystery no more. Thanks for making us one of the best communities on YouTube. See you next episode of Mind Your Decisions, where we solve the world's problems, one video at a time.